When you add a solute to a solvent, the boiling point goes up. The freezing point goes down. There are biological processes like metamorphosis and what occurs in nature. So there are so many natural processes, but what they all have in common is that they're all spontaneous. They're all governed by changes in free energy. Let's take a look at an example. We're going to see if we can apply our first law of thermodynamics equation here to the process of a stretched rubber band undergoing contraction. So we have a stretched rubber band. So this is my reactant. And then it undergoes contraction. There's my product. Okay. What is the change in entropy for that process? Here's the initial. There's the final. What was the change in entropy? Delta G for this process must be negative because it's a spontaneous process. You can't stop the rubber band from contracting. After stretching a rubber band, it feels, well, let's try it. Here's what it feels like initially. You'd have to do this for yourself to prove it, but stretch it and then feel it. It definitely gets hot. So after stretching a rubber band, it feels warm. So stretching a rubber band must be an exothermic process, right? It released heat. And if so, contraction of a rubber band must be endothermic, right? If stretching it is exo, letting it contract must be endo. The enthalpy change for a contracting rubber band must be positive. Because we just said that, right? We said the contraction of a rubber band must be endothermic, so that means it has to be positive for a contracting rubber band. Therefore, the entropy for a contracting rubber band must be, okay, now we have to apply our equation here. We said that delta G is negative, spontaneous process. We said the change in enthalpy for that contracting rubber band is positive. Well, if delta G is going to be negative, delta S had better be a what number? Positive or negative? Positive, right? Because T can't be negative. So in order for delta G to be negative, this delta S has to be positive. Because a positive times a negative will give me my negative number. So we have a positive change in entropy. This occurs. Positive change in entropy. What does it look like at the molecular level? When it's stretched, we have cross-linking in these rubber bands, and they're kind of uniformly distributed here. And then when we let it contract to an unstretched position, the energy gets more dispersed. It's all over the place. So upon contraction of a rubber band, the energy in the rubber band becomes more dispersed. It was uniform. It was uniform here, but now it's more dispersed. Entropy change, positive. Interpretation of free energy. When the Gibbs free energy for a process is what? The process can be used to do work. Less than 0. You want a spontaneous process. So our Gibbs free energy equals W, which is work. How does a physicist define work? Force times distance. So I could be holding this rubber band here for hours on end, and as long as I don't move it, I'm not doing any work. Because I'm applying a force, I'm applying the weight of the rubber band, but I'm not moving it. So I'm not doing any work. Kind of odd, but that's how it works. Calculating a thermodynamic equilibrium constant. So notice, look at this difference. K, before we had Kc. In Kc expressions, all concentrations, even gases, are expressed in units of big M. Now with a thermodynamic equilibrium constant, they have different rules. in thermodynamic equilibrium constant expressions. Notice there is no little subscript c. All concentrations are in units of molarity, big M, except gases, which are in units of atmospheres. And they must be the partial pressure, too. What's a partial pressure? What equation can be used to calculate partial pressure of a gas in a container with many gases? Remember the ideal gas law? PV equals nRT. Let's say we had a whole bunch of gases in this container. We had gases A, B, and C. And we want to know what is the partial pressure of gas A. So what's the pressure that's due solely to gas A? Well, we could talk about the pressure gauge, and that's total pressure, right? The volume of the container that are all in, the total number of moles, the gas constant, and the temperature of the container. But we're not interested in the total pressure. We're interested in the pressure that's due solely to A gas molecules. So we wouldn't use the total number of moles. You just use the number of moles of gas A. So the partial pressure of A would be the moles of A, gas constant, temperature, divided by the volume of the container. Our relation between the standard Gibbs free energy and the thermodynamic equilibrium constant is below. How do you solve for K? So if this is our expression, it has natural log. We need to get rid of it. Remember how? Raise both sides to the e power. Let's divide both sides by a negative RT first. So we'll have the standard Gibbs free energy divided by RT, and it's negative, equals the natural log of my equilibrium constant. Raise both sides to the e, right? Inverse functions, they'll cancel out. So all I'm left with is the thermodynamic equilibrium constant. And that's going to be E to the negative standard Gibbs free energy over RT. So you need to know how to do that, because the only equation I'm going to give you is this one. Which R should we use? Whether we're using this expression or this one, which R do you use? We need to use the R before we've been using this one, 0.0821 liter atmosphere over mole Kelvin. But we're not going to use that one. It doesn't have joules in it. We need energy. Otherwise, this is going to be a lot of work if we use that one. Let's use this one, 8.314 joules per Kelvin mole. That's the R that we're going to pick. What is the difference between Gibbs free energy change and standard Gibbs free energy change? Well, this one's at 25 degrees Celsius and 1 atmosphere pressure for everything. This one, well, it's not. It's not at 25 degrees Celsius and 1 atmosphere. Something changed. One of them is off, or both. Calculating free energy at different temperatures. So all we're going to do is use the tables to get these, because they're standard. We'll use the tables to get our standard entropy and standard enthalpy changes. We'll plug in our new temperature. And make sure it's in units of Kelvin. And then we'll get our Gibbs energy change at that temperature we plugged in Kelvin. Give the expression for the thermodynamic equilibrium constant for the following reaction. Okay, it's thermodynamic equilibrium constant. That means big K. The same as always, products over reactants, just be careful with gases. Okay, so we have hydroxide concentration squared magnesium ion all over 1. Solids don't show up in equilibrium constant expressions. Give the expression for the thermodynamic equilibrium constant for the following reaction. Now we have some gases. So thermodynamic equilibrium constant equals products over reactants. We don't use brackets. Instead, they have to be pressures in units of 1 atmosphere. So we use capital P, and the subscript is the compound. So PC3OH, the partial pressure of methanol divided by the reactants, the partial pressure of carbon monoxide times the partial pressure of hydrogen, but needs to be squared. What is the standard free energy change for the following reaction? Okay, we've done this before, just products minus reactants. Hydrogen bromide, 2 of them, 2 times a negative 54 minus the reactants, hydrogen and bromine, but they're both 0. So a negative 108 kilojoules per mole. What is the value of the thermodynamic equilibrium constant, K? So we can start with our expression. The standard Gibbs free energy is negative RT natural log of K. So do you remember our expression? E to the negative delta G0 over RT will be my K. So this is the expression I'm going to be using. So E to the negative, we said Gibbs free energy was 108 kilojoules per mole. We said delta G0 is a negative 108 kilojoules per mole. But we want it in joules. So that's the same as a negative 108 times 10 to what power? Third joules per mole. Right? This kilo is 10 to the third. So I need to plug that in for my Gibbs free energy. Negative 108 times 10 to the third joules per mole divided by gas constant 8.314 joules per Kelvin mole times my temperature T, that needs to be in Kelvin, and my temperature is 25 degrees Celsius. 25 and 273 is 298 Kelvin. All that will equal K. So we'll have 108 times 10 to the third divided by 8.314 divided by 298 equals, raise it to the e power, about 8.5 times 10 to the 18th. It's a huge number. Does it make sense? It sure does, because look at delta G, a huge negative number. It's very spontaneous. So we expect a lot of product. In other words, we expect a huge equilibrium constant. What is the free energy change at 1,000 degrees Celsius for this reaction? Now we can't use just the table of products minus reactants because we're at 1,000 degrees Celsius. So we have to use that expression that allows us to calculate the free energy change at any temperature T. And what that expression was the free energy change at any temperature T is the standard change in enthalpy minus the temperature times the standard change in entropy. And then we'll have it. So I delta G at 273, I'm going to have 1273 Kelvin. So my delta G at 1273 Kelvin is going to be the standard change in enthalpy, products minus reactants. Negative 36, well 2 times a negative 36 kilojoules per mole minus, and my reactants are 0, so there's my standard change in entropy, or enthalpy, sorry. Temperature, 1273 Kelvin. Now, times my standard change in entropy. Products minus reactants. 199, but watch the units. 199 joules per mole. That's times 2. Right, times 2. Minus the reactants, hydrogen and bromine. Minus hydrogen is 131 plus 152. And that's in joules per mole. Okay, so I need to do a little converting here because I have kilojoules per mole over here. But let's figure out what it is. 36 negative times 2 is about a negative 72 kilojoules per mole minus 1273 Kelvin times my standard change in entropy. Well, that's going to be 199 times 2 minus 131 minus 152, about 115. 115, but that's joules per mole. So I'll have a negative 72 kilojoules per mole minus 1273 Kelvin. How do I get that into kilojoules? Just move the decimal place over how many times? 3. 1, 2, 3. Divided by 1,000. 0.115 kilojoules per mole. And I'll have my answer. Well, negative 218 kilojoules per mole. So that will be my change in free energy at 1,000 degrees Celsius for that reaction. Consider the decomposition of phosgene. Calculate the standard change in enthalpy and the standard change in entropy at 25 degrees. Okay, so part A. Products minus reactants. CO and Cl2. CO is a negative 111. And chlorine is 0 minus reactants. My reactant is the phosgene, negative 220. So 220 minus 111, about 109 kilojoules per mole. And my standard change in entropy, again, products minus reactants. Carbon monoxide, 198. Chlorine is 223. Minus reactants. Phosgene is 284. Plus 223 minus 284, about 137. Remember, that's in units of joules per Kelvin mole. What is the standard change in Gibbs free energy at 25 degrees Celsius? We could use, there's two ways to go about this. We do it that way, or just use the table, products minus reactants. They'll both work. My T would have to be 25 degrees Celsius, well, plus 273. Let's just do the table, it's easier. Products minus reactants. Negative 137 and 0. Minus the reactants, phosgene. And phosgene is just a negative 206. So 137 negative plus 206, about 69. And that's in kilojoules per mole. C. Assume the standard enthalpy change and the standard entropy change are constant with respect to a change in temperature. Now calculate delta G at 800 degrees Celsius. So remember how to do that? Delta G at any temperature is a standard enthalpy change minus that temperature in Kelvin, standard entropy change. So that's going to be, we said enthalpy was 109 kilojoules per mole. Temperature is 800 degrees Celsius. 800 plus 273, that'll be Kelvin. And my entropy is 137, which is 0.137 kilojoules per Kelvin mole. And what do I get? 0.137. Okay, the final answer, I get negative 38 kilojoules per mole for part C. So briefly discuss, well, it went from being non-spontaneous to being spontaneous. At the higher temp, it's now spontaneous. So just a few things have changed. One is we are finding the equilibrium constant from our Gibbs free energy and just know how to manipulate that expression. And another change is we are talking about calculating the Gibbs energy change at different temperatures. So just know how to manipulate those expressions and watch your units and you'll be good.